Welcome to Simpson's rule. So again, the idea here is we are trying to estimate a definite interval. We're trying to approximate a definite integral by breaking, or a definite integral from a to b of f of x dx by approximating f of x with segments of parabolas. For each parabola segment, essentially we need 3 points on a graph of f, and then we can write a parabola through them. So if we have our a and b, and f of x is doing whatever in between, then essentially what we'll do is we'll break the interval from a to b up into subintervals. And then since we need 3 points, we'll actually break each of those up into another subinterval at the midpoint. And we will use these series of 3 points on f to make our parabolas. So again, between any 3 points, as long as the x values are different, we can write a parabola through those points. Let me update my screen. So we model each of these series with the parabola that will go through those 3 points. It's not going to be perfect by any means as I draw this. But so from purple to purple, going through the blue point in the middle is a segment of a parabola. So this is essentially parabola 1. Actually, let me do the most recent one in a different color. So we have our first parabola. Then we have a second parabola. And then we have a third parabola segment in the middle of those dots, etc. And we end with our last parabola segment. And what we're going to do is we're going to instead find the area under each of these parabolas. So note with this graph, those parabolas are fairly close to what the original graph was. And Simpson's rule does tend to get a fairly accurate reflection, especially as we get narrower intervals. So if we have if we break into k parabolas, then we actually have essentially 2k intervals, since each of those parabolas itself is made up of 2 segments, or 2 intervals to get that third point. So if we break into k parabolas, then we need 2k intervals. And so we'll set n equal to 2k. Our delta x is going to be the width of one of the smaller intervals. And so it'll be, again, our b minus a divided by n. To find each parabola, based off 3 points, we have a formula for the parabola and for the definite interval. So we can use a formula. And we will actually skip to the formula for the definite integral beneath for the area under the parabola. So it turns out if x1, x2, and x3 are equally spaced, and if g of x is the parabola that goes through the points x1, y1, x2, y2, and x3, y3, then the definite integral from x1 to x3 of g of x dx is equal to x3 minus x1 divided by 6 times y1 plus 4y2 plus y3. This equation or formula rule can be proven by solving a system of equations in 3 variables, and then you find the formula for your parabola and take the definite integral. It's a rather horrific mess to solve that system of equations, but it can be done. So here we have our definite integral from x1 to x3. So we could have done this really from xi to xi plus 2 as well. So putting this together, with the Simpson's rule idea, we're going to break our interval from a to b. We'll let a equal x0, we'll let b equal xn, and then we'll have x1, x2, etc. up through xn minus 2, xn minus 1. Again, the parabolas are going to run from a or x0 to x2, from x2 to x4, and from xn minus 2 to xn, with our midpoints in the at the odd xi's. So we have our parabola approximations. Update my screen one more time. We have our parabola approximations, and putting together what we just saw, we have that the definite integral from x 2i to x 2i plus 2 of our f of x dx should be approximately x 2i plus 2 minus x 2i over 6 times, we would have f of x 2i plus f of x 2i plus 1 plus f of x 2i plus 2. X 2i plus 2 minus x 2i, that's just 2 times our delta x. Then divide by 6. Again, multiply by f of x 2i plus, oops, sorry, I lost a 4. That should have been plus 4 times f of x 2i plus 1. So f in this line, we have 2 times delta x divided by 6, multiplying f of x sub 2i plus 4 times f of x sub 2i plus 1 plus f of x sub 2i plus 2. Of course, that 2 times delta x over 6 is just delta x over 3. So putting these all together, we have the definite integral from a to b of f of x dx is approximately delta x over 3 times, we would have f of x 0 plus 4 f of x 1 plus f of x 2. That's our first parabola. Then for the second one, we would do plus f of x 2 plus 4 f of x 3 plus f of x 4 plus, and then we would continue this on until we had f of x sub n minus 2 plus 4 times f of x sub n minus 1 plus f of x sub n. So I'm just adding on all of the individual little parabola intervals together. At this point, we have the definite integral from a to b of f of x dx is approximately delta x divided by 3 times f of x naught is just f of a. Then we have plus 4 times f of x1 plus 2 times f of x2 plus 4 times f of x3 plus 2 times f of x4 plus, we would go up to plus 2 times f of x n minus 2 plus 4 times f of x sub n minus 1 plus f of b. Again, here notice my overlap from the first parabola to the second parabola. F of x2 popped up in both. F of x4 would again pop up at the end of the next parabola plus the beginning of the following. And so the only ones that aren't repeated are those odd xi's, which have the 4 all multiplied in front, and then the f of x naught and f of xn. So we have our formula for Simpson's rule. Again, our delta x is b minus a divided by n, where n equals 2 times k, and k is the number of parabolas. Our xi are our usual formula of a plus I times delta x. So this here is our formula for Simpson's rule. So it's not necessarily the most pleasant thing to run through, but at least at this point you can jump straight to the formula instead of having to work through solving those parabola definite integrals individually. So this is Simpson's rule. In the next video, we will go ahead and do an example.